Kia ora and welcome to this overview of 1080 pest control. This lesson looks at this particular topic for the 913989 standard. There are three topics that we offer: the pest control, the fluoridation, and the ocean acidification. So now that we've finished the organic chemistry, we'll look at some of the things you need to look at for this particular standard. So what we'll look at is why we use pest control in New Zealand, what is 1080 and how it's distributed, how does it work, so we're looking very much at the chemistry of that, as well as how does it break down, and again we're looking at the chemistry. Then what are the side effects, as well as what has been done to reduce those side effects, and then otherwise what alternatives can we use instead of 1080. So first of all, why do we use pest control in New Zealand? Now, New Zealand has got a very unique case in that its flora and fauna are very unique to New Zealand. It's got very few mammals. In fact, there are no native mammals apart from two species of bats. Otherwise, we have a lot of native bird life that are unique to New Zealand, and also a lot of the flora, which are the trees and the plants, are unique to New Zealand. Now, with immigration, with the Maori, they brought a certain type of rats. With the Europeans, they brought also rats and possums and stoats that all came over across. Those have now become a major pest in terms of reducing the bird population, because they eat the birds as well as the eggs, as well as destroying the food source, so the flora. The possums, for instance, eat a lot of the same things that some of the birds will eat, and so the bird population is going down. These pests also will eat weta, the native snails, native frogs, lizards, tuatara, and even the bats that we have. Other pests are also a lot of the deer in terms of the grazing of the native flora. Rabbits are also a problem. Also feral cats, and as I said, the rats, stoats and possums, and there are of course others as well. Rats and possums are particularly bad because they are climbers. They are very good ones, so they can access the bird nest high in the tree, so they can't escape. And of course all the ground birds like the kiwi that can't fly are also susceptible to a lot of the pests. The second reason why New Zealand is unique is that it has a very big dairy industry, and cattle can get bovine TB. Now, bovine TB can also affect humans, so cattle have to be tested. So if they do have this bovine TB, then the milk cannot be used for human consumption. And because, as I say, such a major contributor is that if the dairy industry goes bung, then New Zealand's economy is affected in a big way. Now, the bovine TB can be spread by possums, by deer, pigs, cats, ferrets, and even hedgehogs. The problem with possums, though, is they are, because there's so many of them, and they are quite susceptible to this bovine TB and get it, and they tend to die within 6 months, but tends to disorientate them, so they leave the trees, they leave those sort of more dark, they go out into the paddocks and tend to die in the paddock area. Not all of them, but some of them. And the cattle will come along, they'll be curious, they'll sniff at this dying possum, and they will then pick up the infection. Deer are another vector, and so any farmed deer now have to be tested for the bovine tuberculosis as well, so that they don't get it and pass it on. So we've looked at the reasons why New Zealand uses 1080 in terms of that we need a pest control, but why do we use 1080? So first of all, what is 1080? Now, it's a salt that is found in some plants, particularly in Southern Africa, also Australia, and also in Brazil. And it was first identified by a South African scientist, this particular salt, as giving this poison in 1944. The plant is called Giftblaar. It's Afrikaans for poisonous leaf. And it was estimated that 80% of all cattle mortality, that obviously wasn't being slaughtered by humans for meat, was because of the cattle eating this Giftblaar. Animals native to the area don't have the same effect. So, for instance, the indigenous animals in Australia can eat the plant without being affected, but like kangaroos and so on, but any animals that have been brought in to Australia have been affected by this. And as I say, the poison pea in Western Australia is where there's a problem. They actually, if you're bringing in your own cattle, you actually even have to remove the soil because you want to make sure you get rid of all this particular type of plant. Then the name itself comes from the catalogue number. So when it was discovered, it was put into a catalogue of poisons, and so that's where 1080 gets its name. It actually is a salt, as I said, of sodium, the sodium ion, and fluoroacetate or fluoroethanoate. So if you've done your organic chemistry, the two carbons, so that's where the eth comes from, and it's an anion, so that's where that 8 comes from. Anions ending in 8 tend to have oxygen in it, so it's fluoroethanoate because it's got a fluorine as well. So I'm just trying to find right there. Okay, now 1080 or sodium fluoroethanoate is highly toxic to mammals. So it does affect other creatures like birds and fish and so on, but to a much lesser extent. Very poisonous to mammals though. Now before we move on, think of, because you've got to explain the chemistry, what salt is this? What base could it come from? What acid would it come from? So show your understanding of your chemistry. Does that chemical look familiar and that you can understand it from your background of chemistry, or is it something totally new? You should be able to know or recognize that type of salt. Now, following on with what is 1080, first of all, it's produced mainly in the USA and it's processed also in Whanganui. It's also produced in China. There's more and more places making it. And the salt is made by taking an ester, methyl chloroethanoate, and treating it with a salt, potassium fluoride, and then taking the ester formed from that reaction and treating it with sodium hydroxide. So if we have a look here, Wikipedia has a slightly different formula in it. I couldn't find any process at all for this, the one given in Wikipedia, so I think they've simply taken this one and made it a simplified reaction. But this is what is happening in manufacturing. So can you see it's an ester, and use your level 3 chemistry to recognize that that's an ester. And there is the chloroethanoate, so it's methyl. Think of your naming, methyl, because it comes from this alcohol and it's coming from this acid. So it's a chloroethanoate. And it's treated, as I say, with the salt potassium fluoride under very high temperatures and pressures, so 200 degrees and a very high pressure. It's in an autoclave. And what happens is that the chlorine gets kicked out, it gets replaced with the fluorine. So it's a type of substitution reaction. And we get KCl as the leaving group. Now notice the potassium fluoride is a solid, so it's not in solution. So if you think of your chemistry that you have learned now in organic chemistry, first of all, why does it have to be under such high heat and pressure? You are reacting this particular carbon, and that's quite a strong bond, and so you need a lot of energy to break that bond and replace it with something else. Why do the conditions have to be dry? Well, you'll notice it's a solid, it's a very fine powder that's used. Think of why it's such a fine powder. Use your understanding of chemistry. Why isn't it just pellets? Why do we use such a fine powder? I'm not going to answer all the questions. You should be able to think about it with your background in chemistry. We use a solid because Kf, from your understanding of last year's chemical reactivity with acids and bases, fluoride is the conjugate base of hydrogen fluoride. So if there is water involved, you'll get some HF being formed, and we don't want that acid around because you know that acid will cleave an ester. So we don't want it to react with this carbonyl. Remember, this was your reactive center. If you think of your organic chemistry, you want it to react with that carbon. Now, what I've got here is a list of bond energies, which you would have done also in level 2. And notice that the CCl bond is fairly strong, and you've replaced it, though, with a stronger CF bond. Okay, that's just to explain why we need that high temperature and pressure. Now we treat this ester we formed with base, and you think of why base? Well, think of your base hydrolysis of esters. So remember, all esters and amides, the peptide link and the ester link, are susceptible to acid and bases. So if we treat this with a base, we'll get our sodium fluoroethanoate being formed because it gets cleaved over there, and I get methanol coming off. Right, so that is just simply a summary of why we use dry KF and why we treat it with sodium hydroxide at the end. Right, so we've looked at why New Zealand needs pest control and what 1080 is and how it's made. Now we look at how is it distributed. So you'll see this picture on the right. The main distribution for 1080 is aerial, and you'll notice these are these pellets. We'll discuss these pellets in a bit more detail later. This is just a cartoon because in the past a lot of pellets were distributed. Now there's 10 times less being distributed. It's really reduced the amount, but it's still as effective. So it's either used as a cereal bait as shown here, or it's in carrots. So they cut up the carrots and coat it with the 1080. And the why it's used aerially, it's because it's fast, it's efficient. So if they're having a masting year, where in other words a lot of food is being produced by the trees, which will promote a lot of the population of the rats and possums, then more 1080 can be applied to kill off so that there isn't such a population explosion. So that's very quick and rapid to do, and it's also very cost efficient because it's used in very remote areas in particular, and it's more difficult to go in those areas by foot. So that's the main distribution. It's also used in bait stations. Now you'll notice the bait stations are covered. There's a green bait in there. It's covered because you don't want the rain to get onto it, and we'll explain why just now. That's a key point in terms of this 1080 pest control. The other point you'll notice is, can you see it's raised slightly? It is not on the ground. That's to stop the flightless birds from perhaps pecking at it, so it reduces what we call the by-kill. In other words, the animals we don't want to kill, we want to reduce the amount that perhaps will eat it and die. And as I say, bait stations tend to be used where people can go in more easily and set these traps up and monitor them, because you've got to also keep on monitoring these traps. And it can be used, as I say, it's a paste or a gel or the cereal bait, or a carrot bait as well. Now, how does 1080 work? We know it's a poison, but how does this poison work? So just as an overview, it kills because it interferes with the citric acid cycle or Krebs cycle. And Krebs cycle is where the food is converted into energy. So it will affect the energy supply, and so the brain, the hearts, the lungs, and the gonads tend to be affected first because those areas are all high energy use in mammals. And that's why you'll find animals that have eaten 1080 will often have seizures because it affects the brain. And then you'll find the herbivores, so this is a picture of a deer. It tends to be their heart that's mainly affected. You can see the difference between a normal heart that's been killed by a hunter, this deer, and here one that's died from 1080. Carnivores tend to die of respiratory failure, so from the lungs, because that's obviously the way things work. With their hunting, they most probably need more air. The air, I'm not too sure exactly why, but that's the way it sort of works. Because the gonads are affected, that's to make the sperm and so on. So it does also, if you've got sublethal doses but are high enough to cause damage, it can lead to infertility. If you simply have sublethal doses that do not cause damage, the animals can process that and there is no side effect. But if they've ingested enough to cause damage, it can lead to infertility. Right, so continuing with the chemistry, okay, looking at what's in the bait. It's basically cereal, it's got cinnamon added to it, it's got sugar in it, or the glucose, and then it's a green dye, and we'll explain later on in this lesson why it's a green dye. And then it's got the poison, and they found that the best concentration is 0.15%. So 1.5 grams for every 1.5 kilograms of bait. Okay, so what do you know of the physical properties of sodium fluoroethanoate? So is it a solid, liquid, or gas? And is it soluble in water? So first of all, you should know that salts tend to be solids, and carboxylic acid salts are exactly the same. So it is found as a white powder. So when you make it, it's a white powder. If we just use the carboxylic acid, in other words, fluoroacetic acid or fluoroethanoic acid, it would also be a solid, but its melting point is around about 30 degrees, which means on a hot day it would tend to become liquid and perhaps drip out. So you don't want it as just a fairly low melting point. You want something with a much higher melting point that'll stay as a solid. So you can easily work it into the bait and it'll be stable and stay in the bait. So that's good chemistry, thinking of how the properties can be used in making and distributing this poison. The other thing you've got to look at is its solubility. So you should know from your solubility rules that you looked at in 3001, you should know that it's soluble, because remember, group 1 salts are all soluble. Okay, you'll notice with these exceptions of all these others, it says all insoluble except for group 1. So sodium fluoroacetate, because it's a sodium salt, it will be soluble. What did not appear also in this table, though, is actually acetates or ethanoate salts are also all soluble. So this is a soluble ion and that is a soluble ion. So sodium fluoroacetate is very soluble, and that is a key point in its chemistry. And so it'll dissociate very readily. Okay, then look at the sodium and the fluoroacetate, both part being soluble. And you should be able to write the equation for that. And there it is. You can do it in a more condensed form. Right, so we made the key point that it's soluble. First, that it's a solid, so we can use it easily in the bait and it'll stay stable in the bait. And now it's soluble. But how does it actually work? We've said it affects the Krebs cycle or the citric acid cycle. So this looks very complicated, but the key points is this over here. We've got this coenzyme A in mammals, and what will happen, it attaches itself to an acetyl group, so the ethanoate part. So remember, when an animal ingests sodium fluoroacetate solid, it will immediately dissolve in their system, because we've got a lot of water in our system, so it'll dissolve in our stomachs and it'll go into the blood very easily because it's soluble. Then what will happen, the fluoroethanoate part is will get attached to coenzyme A instead of the acetyl part, or the ethanoate. Acetyl is just a common name for ethanoate. Then that coenzyme A will turn it, usually it turns the ethanoate part into the citrate anion, but now it'll get turned into the fluorocitrate. So there's going to be a fluorine on one of these carbons over here. That means it needs to go through the next step, but this is where it freezes. The enzyme, because all this is done by an enzyme process, the enzyme that does this can't carry on. The fluorocitrate stops this process. So we can't get all this energy coming off here. Okay, so that's the jamming part. And if this jams, it gets stopped here, there's two effects. First of all, we don't get the energy. So we die of not having, or the animals die of not getting the energy, so their brains don't work and so on. Also, you get a citric acid buildup. Now, when you do the 3060 series later on, then you'll notice the importance of citric acid because it's a very good ligand for calcium. And calcium, you know, you need for your bones, you need it for brain function, so that you get poisoned by having too much citrate in your body. Okay, so we basically said here that the enzyme is jammed, okay, and the citric acid builds up, and as I say, when you do the 3061, you'll know what citric acid does. It forms a complex ion, and if it complexes the calcium, then you don't have calcium available for doing its function in the body, and so you can get seizures. Right, now we were talking about acetate and fluoroacetate. What the slide is pointing out is the similarity in shape. So there's the acetate, there's the fluoroacetate. Very similar in shape. This is just slightly bigger than that, and of course it's much more electronegative than this carbon, but otherwise very similar. Similarly here, this is actually citrate. You'll notice there's 5 carbon atoms in a row with a carboxyl group there, a carboxyl group there, and a carboxyl group there with the hydroxyl here. This is exactly the same, but instead of the hydrogen, it's got the fluorine. So this is how it can fuel the body, because it is so similar in shape, so it can lock onto the enzymes because of the similarity in shape. One thing you should also have learned from your organic chemistry is enantiomers. They are very important in the body and how it works. So do you notice that there are more chiral, in fact, are there any chiral centers in this molecule, in this citrate? Okay, are there any chiral centers in this fluorocitrate? You should be able to spot the chiral carbon and also discuss it, because that's the way it will also lock on and stop any further involvement. Right, so here is what happens with that achotinase. There is my citrate, and what will happen, the enzyme takes off the OH, the hydroxyl group, and a neighboring hydrogen. So you can see the OH is gone and the neighboring hydrogen is gone. Can you recognize this as an elimination reaction? It doesn't need high heat and temperature as you would do in a laboratory, simply because it's all enzyme driven. So water's taken off, and then what happens, the enzyme then takes the OH, and where it was on the central carbon, it now makes the isomer by putting it on the second carbon. So, and that's the way how it carries on in the circle, the Krebs cycle. So basically what this acatinase enzyme does is takes the OH and puts it on to the other carbon by making an alkene intermediate. So it goes citrate, we've got the cis-acatinate, and then it goes on back to the isocitrate, which is when the OH is on this carbon over here. When I've got, and there I'm just trying to show the alkene. So that is what it looks like there. The double bond is over here between these two carbon atoms. Right. Now, when I've got the fluorocitrate, it does this without a problem. Okay, it makes the double bond, just like it did over there. However, in the process, it removes the fluorine and it replaces it with an OH. And so we've still got this chiral compound over here, and this is what locks on. Just the particular shape of it is enough to make it lock on by hydrogen bonding and its shape, and it won't come off. And when it won't come off, this enzyme is not now available to go and convert more citrate to the isocitrate, so the system stops. Okay, so here we can carry on to the isocitrate, here we can't. Right, so we've looked at how it is made and how it works in the body and how it kills. Now let's see what happens in the environment, because not all fluorocitrate gets eaten by animals, and what happens to the rest of it. Now, as I said, it's really important the fact that it's soluble. Because it's soluble, it can get absorbed easily into our blood and get moved around. It's also soluble to get rid of it in the environment. So when the pellets get wet, when it gets washed out, then it gets quickly diluted because it gets dissolved very readily out of the pellets and gets quickly diluted with the rain and in the water when it gets washed into the waterways. We have certain aquatic plants that will convert that fluoroacetate, and it defluorinates it, so it makes it non-toxic. We also have microorganisms in the soil that do exactly the same thing. And there have been lots of tests about it, of how long it takes. And so it can defluorinate in a day at 23 degrees. Now notice that's quite warm. It's warmer than a lot of New Zealand is. So you have to test it at colder temperatures. And do you notice that it takes longer? So think again of your chemistry rates of reactions. Why does it take longer? Okay, when should you do the 1080 distribution? So that's all what you've got to consider. And then, as I say, any 1080 that doesn't get into the waterways and goes into the soil, that is degraded very easily to 2-hydroxyethanoate. See if you can draw that compound, and fluoride. So fluoride is being released into the soil and into the water, because obviously it can leach from there into the water. And that can also get taken up with plants, because some plants bind onto fluoride very easily. Tea bushes, for instance, absorb a lot of fluoride out of the soil. But again, a lot of cities in New Zealand add fluoride to the water, so there could be discussions about that. Not so much in this task, but for you to think about. Now, as I said, can you draw the structure? And also, can you write that equation? I'm not giving you everything. And then, as I say, there's been lots of laboratory experiments done using controls of boiled water where there are no microorganisms in there, and water from rivers, and water that contains these plants. And they found that 50% of the 1080, 50% is just simply a way of a standard. So whenever they do measurements, it's always when 50% has disappeared. So when 50% of the 1080 degrades, and they found it takes 10 days to be defluorinated at 23 degrees, and if you do it at 10 degrees, it's 30 days. So again, you've got to think of why longer. So any 1080 that's been washed out of the bait isn't a problem, in that it will disappear. It'll be gone within a month, okay, even at low temperatures. The secondary poisoning, this is when an animal comes along, eats the bait and dies. Think of it, once that animal has eaten the bait, can the poison get washed away, or is it trapped in the carcass? Will it kill any animals eating that? And the answer to that is, of course, it can't get washed away because the poison is trapped. So it means any animal coming along and eating the dead possum or so on will get poisoned. Now that is a positive thing in some aspects, because stoats who don't like eating the bait because they are carnivores, so they won't eat the pellets, but they will eat the dead possums and the dead rats. So it is a way of killing off the stoats as well, the stoats and the weasels. Otherwise, there's no way of killing those animals off. So what would happen is you have a 1080 bait, the animals will eat it, and then the stoats come and eat the dead animals. They've got here for the 1080 free bait drop. That was also done as a control, and if you do that, then rats think, it's okay to eat, nobody's dying around there, and then they do the 1080 drop, and then they're so used to eating the cereal bait without it being a problem, and then of course they get killed off. However, as I said, we want to have animals poisoned by eating the dead the dead creatures, but of course it's not just the stoats that can eat the dead animals. There are other creatures as well, and one of the major problems is dogs, because dogs are very susceptible to sodium fluoroacetate. Notice that they only need 0.06 of a milligram per kilogram of their body weight. So they don't need much, and they can die from it. You've got, by looking at this per kilogram, is, remember, a small bird like a silver eye looks as though it is a lot less susceptible than a dog, and in a way it is, because it needs to eat a lot more per kilogram body weight. But if you think of the size of a silver eye, it's very much smaller, so it only needs to eat even much less than a dog for it to be poisoned. So think of the size of the animal to see how susceptible it is. Now you'll notice here's a black robin, and they tend to be attracted to the bait, so that's also where bait stations can be good, and we'll look at ways of how they've tried to reduce that as well. Right, so what we've got here is also showing the carrot bait, and in the past it used to be very small carrots, and so animals could eat that very easily, birds could eat that very easily. So very small carrot baits aren't used anymore. Also the carrots being red, and also the original bait was also red. Red attracts birds, so blue ultraviolet attracts insects, red yellows tend to, especially reds, tend to attract birds. That's the way their vision works. So Weka, for instance, would be attracted to the pellets. They'd also be attracted to the carcasses of the animals killed. So any dead rats, they would come along and go, oh, lovely, yummy food, and would also be killed by that. And so there is a bit of biokill of this. However, it's sort of weighed up in that, yes, some of the animals are being killed that we don't want them to die, some of the birds, but by killing off the pests, the remaining birds can still raise more chicks than if the pests weren't being killed off. So it's a bit of a balancing act. And we'll look at ways of how they've tried to reduce the biokill. Now, fish also can be affected because mammals are the most susceptible, but as I say, birds, reptiles, and fish can be poisoned as well. But they're not as susceptible, and they've been monitoring the water, and they've just found that any concentration of fluoroacetate has been below the lethal concentrations for the trout and other fish, so for the sports fishermen and so on. And they've also pointed out if you're having a cup of tea, as I say, tea plants tend to absorb fluorine in the water and fluorine in the soil, and they'll make fluoroacetate themselves. Very, very small amounts, of course, but if you drink tea, you must be getting more fluoroacetate in your body than if you drank the river water. Right, so let's look at what has been done to reduce the side effects, because we don't want birds to be killed and other animals to be killed. So first of all, we're trying to stay away from the red mist, which attracts birds. So the cereal baits are green, and the carrot baits tend to also be green. Cinnamon has been added, and that tends to stop kea from eating them. Cinnamon does attract the black robins, unfortunately, so it's made in different ways. Cinnamon also masks the smell of the 1080, so the possums tend to eat the 1080 bait a lot more easily if it's got cinnamon in it. As I say, pellets tend to be used now rather than carrots, and they also have a longer shelf life, and also when they get in the environment and when they get wet, so say they've been done in an aerial drop, they're not under a shelter, then it washes out easily from the cereal bait, and so won't hang around in the environment for very long at all if it's done through an aerial drop. Also, the bait sizes are now much bigger, so it's much harder for the birds to move them around or to eat them very easily. In the past, they used very tiny bits, and it's called chuff, and that is not used anymore. You also have less being dispersed aerially. In the past, it used to be about 30 kilograms per hectare, so there were cases where, for instance, the wind would take this, or the way it fell down a cliff face, and you'd have high concentrations of 1080 cereal bait, which the deer would come along and eat, and of course kill them off. So now it's a lot less being distributed, so you won't get these clumps being formed, or not as much. Deer repellent has also been added to some species, and there's been no record that it's preventing the possums from eating it. So that's it. I can't spell deer. That should be D-E-E-R. Okay, and that's done particularly where local hunters have requested it to be added. Aerial drops are still being used simply because in very remote areas where it's steep terrain, people can't get them very easily. Possums can live there, but humans can't get to them. So that's where aerial drops are being used, and not so much in other places. And the timing. So winter and spring is where it's used. Yes, it's cold, so it won't break down as quickly, so that's a minus point. The plus point is, of course, that's the rainy season in New Zealand, so of course that helps. If any 1080 has been dropped, it washes out of the cereal bait very quickly, and it breaks down because it's been washed out. It's the cold, dry conditions that allow the 1080 to hang around. So in bait stations, that's fine, because you want it to be there a lot longer, because people are not going to be visiting the bait stations very often to replenish it. But when it's aerially done, you want it out of the environment as soon as possible. And in the winter, springtime, if you've killed off the pests there, it just gives a bit of time for the birds to raise their chicks before the pests can reproduce and get going again to kill off the birds. Okay, what are the alternatives? If we don't want to use 1080, what can we use instead? So there is this particular poison. It's a second generation anticoagulant, brodifacoum. It's slow acting, so they don't become bait shy. So what will happen is they can eat the poison and they can wander off, and 2 weeks later they'll start being affected by it. So they'll keep on coming to the bait. There won't be dead animals by the bait. However, it takes a long time to break down in the environment. It also bioaccumulates. In other words, anybody eating that it's like the DDT, it will bioaccumulate. And you don't want that. You want it to be able to be broken down. And there's also greater risk of biokill. In other words, the non-targeted species eating it and killing those off. Cyanide is another one. Very, very lethal, much more lethal than the others. So it's a quick death. So it's, if you like, more humane because they don't suffer as much because it's such a quick death. However, it doesn't, it kills everything off. So at least the 1080 is more focused on mammals. Cyanide can kill everything. So the native species, humans are much more at risk. Also, because it's so quick acting, you'll get dead animals around the baits, around there, which means that other animals will not come near there and eat it because they become bait shy. Then we've got one that leaches calcium, so in a way a bit like that with the citric acid buildup. Remember I said it attaches onto calcium. This does the same sort of thing. It doesn't bioaccumulate, breaks down readily. There's little risk of biokill, but it doesn't kill stoats, because remember I said stoats will only are carnivores, and so they won't go for the baits. And it's a pretty horrific death as well. Here's another one, and that does kill stoats and weasels and feral cats. Okay, there's little residue left. However, you can't do aerial drops with it. It's done mainly for the carnivores, and so it doesn't kill the possums and the rats because the poison doesn't work very well on them, and it's got to be ground intensive. You can't do aerial because it doesn't break down very readily. It does the same sort of thing as cyanide, where it stops the O2 being absorbed in the blood. Trapping doesn't involve any poisons, so it's really great as far as that goes. You can trap possums, you can trap stoats, you can trap a lot of animals that you want to trap by shaping your trap to suit. You can set the traps above the ground so you don't get the kiwis and so on that have been killed in the past. The issue is, though, the traps have to be checked regularly, and you have to be able to access the rugged terrain, which is not really possible in the very rugged terrain. So if you don't trap the whole area, it means there are areas where possums can breed and then move out and kill the birds all the time, so it's not a final solution. What they're working on at the moment is biological control. However, this will also involve controversy because it'll very likely involve genetic engineering. So that is a lot of the papers that I've gotten Otto summarized, but I still want you to go and look at those papers, but at least you know more or less what to look for. We do want a good level of detail, and of course it must be in your own words. It mustn't just simply be a copying of this video. This video was just made so you can see the depth we want you to go into and the type of chemistry we're looking at. Right, goodbye and all the best.